Good afternoon, everyone. I hope my screen is visible.
Good afternoon, sir.
Yeah, good afternoon. Okay, so let us start. In the last lecture, we have discussed about three different resource allocation algorithm, which you can implement using Hygia Open Resource Manager. So, in order to install Hygia into your system, you have to install Ubuntu, okay, or any platform, Linux platform, right? And there is a you can type in Google Hygia Open Resource Manager. A step-by-step manual is provided. You can use that manual to run leases using Hygia default resource allocation, right? Algorithm. But if you want to implement the algorithms which are improved over Hygia Resource Manager, then that algorithm code you have to write. So first you try with the default algorithm. Once you are habituated with the environment, you can modify the code. So in today's lecture, first we will discuss about the fairness-based algorithm, because you know about different type of leases that are used in cloud. So we have to know about what about the fairness when we assign such leases to the resources, right? Then I'll tell you a very famous algorithm that is used in mathematics, that is called as Hungarian algorithm. Okay, that algorithm actually solves if the input is in the form of a matrix. It may be in the form of a square matrix, or it may not be in the form of square matrix. Okay, but finally you have to make it is a square matrix by adding some dummy elements, so that you can find the resource allocation matrix from that particular algorithm, right? So one by one we will discuss. Let us go for first fairness based algorithm. You have seen different type of leases, although in while discussing this resource allocation algorithms, I only focused on the deadline sensitive leases. But you can also try the immediate leads. You can also try the best effort leads, other leases that we have discussed in the previous lecture. So if you consider only two type of leases, like first one is advance reservation, second one is best effort. You know, advance reservation lease is having a specific start time and end time, or we can say it is having a specific start time and a specific duration. Like if you go for best effort lease, there is no specific start time and there is no specific end time. Rather than you are given with a duration, whenever your resource becomes available, you can schedule the best effort leases, right? But if there is, again, also the advanced reservation lease is having more priority over the best effort lease. That means if a best effort lease is executing, if it is a primitive best effort, on arrival of the advanced reservation lease, the best effort lease is preempted. Okay, and once the advanced reservation lease is completed, then you can resume the work of the best effort lease in the same node, right? So if there is a frequent arrival of advanced reservation lease to the system, then you can see AR can print the best effort lease, and best effort will never get a chance. Okay, we will never get a chance to uh, execute in the system, right? Suppose I will take an example of a single processor system, right? Suppose in a single processor system, first you have assigned a B lease, right? But while B lease is executing, suppose a AR lease is arrived here. What you have to do? You have to print B. So at this point of onwards, you have to start AR. Let's say the AR is completed here, right? Let it be a advanced reservation lease is executed by printing B. So at this particular period of time, you have to resume the best effort lease, resume the work of best effort. But at this time, another AR is coming into picture. And again, the execution is deferred. The best effort task execution is deferred. So it is deferred to this particular period of time. Again, if a AR is coming, again it is deferred. So we can see in this scenario, if the frequent arrival of AR happen, then B tasks are not getting a chance. So which says that there is no fairness among a set of leases, right? You can take the example of other leases also. For the simplicity of example, I considered here advanced reservation lease and best effort lease. So if there is a frequent preemption happen to best effort lease, it leads to overhead. It also leads to starvation among the best effort leases. Okay, they will never get a chance. So definitely they will face the starvation problem. Therefore, and significant problem is to how to schedule this AR lease and B lease such that starvation among these leases are reduced up to some extent, right? So we have to make some trade-off between AR lease and best effort lease. Like some of the best effort lease may be converted to advanced reservation lease, or some of the effort lease can be converted to non-primitive best effort lease, right? So that you will not face any problem with respect to fairness, right? Like if you see a temple, right? If you consider a temple as an example, suppose in a temple you have two queue. One is male queue, another is called say female queue. Okay, a male queue, another is female queue, right? Suppose I'll give priority to the female queue. Okay, and I'll say, let's say once the female queue is empty, then only I'll give a chance to the male queue. Okay, or vice versa case, whatever may be, right? So what happened, the alternate queue is going to be face starvation, right? They will face starvation. So in order to avoid that, what you can say I will give the ratio is 1:2. Okay, that means I will allow one male followed by two female, right? Suppose female queue is long, then you can follow 1:2 order. Suppose male queue is long, so you can follow 2:1 order. Two male followed by one female. So you have to design some kind of strategies, okay, in order to avoid the starvation among the advanced reservation list and the best effort list. Okay, so we can address this particular problem in a heterogeneous environment and at least homogeneous environment. So you know, in homogeneous environment, if the number of processors are there, they are having same configurations. When you go for heterogeneous processors, then you can see each and every system is having different configurations, right? So we want to develop an algorithm in order to provide fairness among both advanced reservations and best efforts. And this problem is not only targeted to the multi-processor system or multi-cloud system, but also it can be with single cloud system as well. Okay, so this particular algorithm allows, why we need fairness algorithm? Because that algorithm should capable to allow some of the best effort leases to be scheduled before the AR lease. Some B leases you at least you have to provide the chance to execute in the system instead of the all the AR leases in order to avoid the starvation. Okay, so it should be done in a regular interval. Let's say you have permitted 80% of the AR followed by 20% of the B. Okay, again 80% of the AR, another 20% of the B. So B will not face starvation. Okay, a lease is less priority does not mean that you will make its execution delayed for infinite period of time. That is not good, right? So, however, in order to find this particular interval depends upon arrival rate of advanced reservation list and best effort list respectively. We have to look into what is the arrival rate of advanced reservation, what is the arrival rate of B. Like I mentioned you, if it is a male queue is long, then you can consider 2:1. If female queue is long, then you can consider 1:2, right? So it really depends upon how many AR leases and B leases arrive to the system. For example, if you see here, at the time t is equal to 0, assume that there are 8 advanced reservation leads and 20 B leases are arrived into the system. Okay. So you can see by looking into this number, you can see number of B leases are always more, right? Because B lease is less costly, right, in comparison to AR leads. Or if you see this particular example, the number of B leases are very, very high. So if there is no fairness, assume that there is no fairness algorithm. Then what you have to do? First, you need to complete 8 advanced reservation leases. Then you will execute the 20 B leases. Right? So this 20 B leases has to wait until unless 8 AR leases are complete. Okay, so which leads to starvation among the best effort leases. So let us see for this particular problem, if you want to represent the advanced reservation lease, how it will be represented. So in AR lease can be represented in the form of a 3 tuple. One is S, which is nothing but the start time of the lease. For example, I will say start time of the lease is 9 a.m. P is nothing but the execution time of the lease. So I can say execution time is 1 hour. Okay. So obviously the period is 9 a.m. to 10 a.m. Right? And N indicates no preemption. Because obviously, advanced reservation leases are highest priority and advanced reservation lease cannot be preempted in between. Moreover, you can say an AR lease cannot be preempted using another AR lease. Right? One AR lease is executing. So if another AR lease is arrived to the system, so you cannot preempt that AR lease. Okay, because it is non-primitive in nature, and the same category of the lease or same priority lease, they cannot preempt each other. Right? So now, in contrary, if you look into best effort lease, right? No preemption, let's say I'm writing 0. 0 indicates, let's say, no preemption. So this is the 3 tuple. But when you represent the B lease, we represent the execution time. Let's say the execution time is 1 hour. Okay. ST is here your starvation time. Let's say I will say this B lease has submitted now and it has to complete it before, let's say, 11 p.m. or I can say 23. To represent in 24 hours format, I can write 23. Okay, that is my starvation time. That is up to this particular period of time, a B lease can wait. After that, if you are not giving chance to this B lease, it will face an starvation problem, right? And preemption indicates 1. Okay, if I represent no preemption is 0, I represent no preemption is 1, right? So this is the tuple representation, and generally B lease is primitive in nature, where AR lease is not primitive in nature. So let us take an example to understand why actually we need this fairness algorithm. But for this, let me take a single processor system so that you can easily understand. Later point of time, if you are interested to know about more about, you can think about multi-processor system or multi-cloud system. So let us consider an illustration with a single virtual machine, or you can say single cloud. So at t is equal to 0, okay, when time is equal to 0, this is your t is equal to 0, there is a best effort lease reached to your system, which is 5, having 3 tuple 5, 50, and p. 5 is the execution time. 50 is your, or you can say ST is nothing but the starvation time, it is 50, and P means it is preemption. Or you can write 1 for preemption, 0 for. You can write 1 for preemption and 0 for no preemption, right? So BI start the execution because there is no lease in the system. There is no B lease, there is no AR lease at t is equal to 0. This is the only one lease that is available in the system. So I have started the B lease. So it requires 5 time. So it has started from 0 and it is expected, if it is started at 0, it is expected that this lease BI is going to be completed by 5 minutes of time, right? But we have experienced that when t is equal to 2, and advanced resolution leads is reached to the system. Again, AR also is represented in the form of a three tuple. So what are the tuples? AR means you can say this 2 is nothing but the start time. 5 is nothing but the execution time. N is means there is no preemption, or you can represent it with 0. It is represented as preemption is represented as 1. So AR lease is arrived, and it is, let's say, it is a primitive based effort. Primitive based effort means once AR lease is arrived to the system, you have to give chance to AR lease. So at 2 unit of time, I have printed this BI lease. So you can see here, at 2 unit of time, BI lease is printed. Then you have to immediately start AR lease. If you start AR lease will take how much time? It is going to take 5 unit of time. So it is expected to complete at 7 unit of time. Okay, BI is printed, and once a task is printed, its corresponding disk image is stored by that virtual machine. Because you have to again resume, right? When you execute BI and it is not completed, you have to create its disk image. That disk image you have to store, right? You have to store in the virtual machine, because you have to resume that once the AR is successfully completed. So once the AR AI completes its execution at t is equal to 7, right? When the time instance is equal to 7, AR lease has completed its execution. So at that time, what you have to do? The B lease is resumed, subjected to no other AR lease is arrived to the system. So here you can see the BI lease has resumed its execution at 7 unit of time. Okay, it has resumed its execution at 7 unit of time. So how much time it require? B require 5 unit of time, 2 unit of time is already given here. So another 3 unit of time, okay, another 3 unit of time you can give after 7. So this BI lease, which is expected to complete by 5, now it will complete at the 10 unit of time, right? Subjected to not arrival of any other advanced reservation lease. For example, if I say at 7 unit of time, some AR leases are arrived. So let us see. Let us assume that t is equal to 7. There are two B leases. One is BJ, another is BK, and 4 AR leases AJ, AL, AM, and AK. These are the 4 leases that is arrived to the system. So we'll look into the AR first, right? See, if the AR is started at 7 unit of time, then we will not give to B. But you can see this AR lease will start at 8 unit of time. The next AR lease is will start at 15 unit of time. Next is 18 unit of time. Next is 20 unit of time. Right? So what I'll do, I'll continue up to 8. So the B lease which we have started here and it has completed 2 unit of time here. Now it is again executed for 1 unit of time. Okay. So but it requires how much time? It requires 5 unit of time. You can see here it requires 5 unit of time. 3 unit of time you have given up to 8. Now I'll start this advanced reservation lease, right? So this advanced reservation lease, if I start at 8, it will continue up to 5 unit of time. So it will complete at 13. So now this AJ is completed. Okay. Now again the next AR is going to start at 15. So 13 to 15, you have another 2 unit of time. So you will resume the execution of the same BI lease, right? So now it is completed at 15 unit of time. So you can see one B lease, that is BI, which arrived at 0 unit of time. It is expected to complete by 5 unit of time, but actually it is completed at 15 unit of time. So this is the main issue what we are facing in the case of best effort lease. That's why there is no fairness when you compare AR lease with the B lease, right? Now at 15 unit of time, I can start AK. So it is going to take 3 unit of time, 15 to 3, 15 to 3. So it is 18. Now 18 unit of time, another AR is arrived. So it will take 2 unit of time. So 18 to 20. Okay. Now at 20 unit of time, another AR is arrived. So it will take 3 unit of time, 20 to 23. Right. So all the AR leases are completed at 23 unit of time, which are arrived at t is equal to 7. Now you are left with another two, you can say, best effort leads, which you can start executing after 23. So I also told you, right? You have to put a queue for B leads. So earlier there is BI is in their queue. At t is equal to 7, you will put BJ and BK into the queue. But at 15 unit of time, BI is completed, so it is removed. So now you have BJ. So BJ you will give chance. It will take 3 unit of time, so it will complete at 26. BK, it is asking 1 unit of time, so you can start after 26 and it will complete its execution at 27 unit of time. So what this example actually says, this example says that if there is a frequent arrival of AR leases, like here you can see there is a frequent arrival of AR leases in this period of time. So we are not giving chance to the best effort ratio. Okay, in that case, it may face the fairness problem. Okay, or you can say there is no fairness among these two type of leads. So B leases are always going to face the starvation. So that is the main issue. So this is the problem actually. You have to consider m different clouds, right? If you want to go for a multi-cloud environment to implement this one, so you have to consider there are set of m clouds, C1, C2, C3 up to Cm, and there are k independent AR tasks. So these tasks are not independent, or you can say these DJs are not independent. But I'll tell you some examples in later classes. You can see there is a dependency between AR tasks. So they are independent AR tasks. Similarly, we have L independent B tasks. So they are represented from T1 to Tk and Tk plus 1 to Tk plus L. Okay. So there are set of AR tasks are there, set of B tasks are there, right? So a task set T is the permutation of the independent of AR and B. Okay, so it may be any combinations. You can mix the AR leases, B leases, because we don't know what is the order. The order may be anything, but the task set is nothing but union of all the AR leases and the B leases. So what is our problem here? Our problem is to assign the AR leads and B task to the cloud such that fairness among the tasks can be achieved. Okay, so you have to assign AR leads and B tasks to the cloud. If there are m clouds, you have to schedule to m clouds. If there is one cloud, you have to schedule to one cloud, such that fairness among the tasks can be achieved. And this problem is restricted with a set of constraints that you have to actually follow. Okay, first constraint says that Ti should be the relationship between Ti and Ti plus 1. If you see, it says that A is executed before B. That means Ti is executed before Ti plus 1. So there is a specific notation we have used here. That notation signifies first you need to execute the task Ti, then you need to execute Tj. The order cannot be changed. Like whatever order it is given here, the order you cannot change. The order you have to follow. Only thing is that B task can be printed. That is the only option you have. Similarly, Ti and Ti plus 1, the relationship you can see here where K plus 1. So that is a order right here. If you see K minus 1 means we are talking about AR task. If I take I value is in between K plus 1 to KL plus minus 1, so I am talking about B task. Okay, for B task also you have to follow. Okay, B task also you have to follow that particular order. Now, if you see Ti and Tj, there are two tasks, so they can be executed in any order, right? Like if I take a AR task, if I take a B task, so they can be executed in any order. There is no dependence. But here there is a dependence. If I pick two AR tasks, there is a particular order. If I choose two B tasks, there is a particular order. But if I'm taking a AR task and B task, they can be executed any order. Okay. Okay. Now let us see this algorithm. Try to understand how to solve this fairness ever task allocation, or we call this FATA algorithm. So we consider. Okay. So we consider here total number of AR tasks. Like all the tasks are put in a queue, right? Generally, tasks are put in a queue, and queues we are maintaining for and executing in the first come first serve order. So in the queue, you may have a AR task, you may have the best effort task, right? So suppose CAR is called as count of AR. Okay, how many AR tasks are there? That is total number of AR tasks present in a waiting queue. That is represented as CAR. CBE is nothing but total number of B tasks in the waiting queue. Okay, like previously I told you, there are 8 AR tasks, there are 20 B tasks. Okay, there are 8 AR tasks and there are 20 B tasks. And J is equal to 1. So we consider that J is equal to, there is a variable that we have considered is equal to 1. So until unless the waiting queue is equal to null, you have to iterate, you have to schedule one by one. Okay, so first I have taken WQ. Let's say in my waiting queue, initially at a t is equal to 0, we have 8 plus 20 tasks. 8 means 8 AR tasks and 20 B tasks. So total task we have is 28. So if waiting queue is equal to TAR, I'm checking waiting queue. When I is equal to 1, I'm checking the first element that is present in the waiting queue. If it is an AR task, then I will increase the CAR value. So suppose this is an AR task. Okay, this is a B task. This is a AR task. This is AR task. This is a B task. This is a AR task. This is a B task. B task. So when I say WQ of I and I is equal to 1, so it is an AR task. So CAR value, which is initialized to 0, now increase to 1. Right? Now I value when it is becomes 2, I am looking into this index. So it is in a B task. So WQ of I, WQ of 2 is equal to TR is false. So CBE, okay, it is which is 0 earlier. Now it is increased to 1. Now I is equal to 3. So we are looking into this one. It is an AR task. So count is increased to 2. Next, when I is increased to the next value, the AR is increased to 3. Like that, if you continue, let us assume that CAR we are getting 8, CBE we are getting 20. So this CAR and CBE, if you mix it, that is nothing but the total number of AR and B tasks in the system. So by scanning a waiting queue, you will come to know how many AR leases are there, how many B leases are there. Okay, because if you know the how many tasks are there, then only you can apply a fairness algorithm. Like I told you, in a temple we will follow 1:2 order, or we follow 2:1 order, right? If male queue is small, then we will follow this one. If female queue is small, we will follow this order. How you have decided it? By looking into how many peoples are there in a particular queue, right? Otherwise, it is not difficult to determine uh, how many peoples are there, or how many. It is difficult to propose an algorithm, fairness-based algorithm. Now, if you go for rate of arrival, here we are calculating rate of arrival. For example, CAR is equal to 8, CB is equal to 20. Now I am calculating RAR. RAR is nothing but CAR divided by CAR plus CB, that is 28. So if you calculate 8 divided by 28, how much you will get? Can anybody calculate? So you will get 0.28571. Similarly, if you calculate RBE, it is nothing but 20 divided by CBE divided by CR plus CB. So that is 28. So if I do 20 divided by 28, so you will get 0.71428. What it indicates? By looking into this rate of arrival, you can say number of B tasks are more than the number of KR tasks. Now I am checking if RB is greater than tau. Okay, RB is greater than tau. Then what is tau? Tau is a threshold. Then how many leases you want to give priority over the AR leases. So if RB is greater than tau, so suppose I am taking tau is equal to 20. Okay, that is 0.2. So RB value is 0.71. So it is greater than tau. So I have to make RB is equal to tau. That means RBE value is now reduced to 0.2. Why I am doing? Even if the number of BE leases are quite more, but we can accept only 20% BE lead for a fairness. Because I cannot make fair to 100% of the BE lead. Because we know BE has less priority. So we'll give more priority to AR leads only. Right? But 20% of the B leads will give more priority over the AR leads. That's why RB value is equal to tau. Now we have to follow this particular procedure. Like I calculate R is equal to RAR divided by RB. What is RAR? RAR is 0.28, right? Something divided by RB is 0.2, right? So if you calculate it, you will get 2. Right? If I take, this is a ceiling function, right? This function is a ceiling function. So ceiling of 1.01 is also 2, right? Ceiling of 1.99 is also 2, right? But if you calculate, this is R. If you calculate R dash, R dash is nothing but tau divided by RB. Tau is your 0.2 divided by RB is, okay, RB is also 0.2, right? Which is equal to 1. Okay. So what it indicates? R indicates the rate of dispatch of AR task. R dash represents rate of dispatch of B task. Okay. So if you take AR task, right? Sorry, if you take RB, before assigning this RB is different, not this one, updated RB. So I can make like this. For example, let me delete this one. I will take the old RB value, that is 0.7. So if you do 0.2 divided by 0.7, you will get 0 point something. So you will get the ceiling function is 1. Right. This RB is not equal to the tau value. Although we have assigned it, you can give a different count here. Okay, different notation here. This RB is nothing but this value. Okay, not is equal to tau. Okay, so if I do 2 divided by this RB is 0.771. Okay, so 2 divided by 0.7, 0.2 divided by 0.71. How much you will get? First one is 0.28 divided by 0.28 divided by 0.71. So it is coming 0.39, so it is 1. Second case, it is 0.2 divided by 0.71. So you will get again 0.2. So it is also 1. What it indicates? We'll dispatch one AR task followed by one B task in order to make the fairness. Right? So this RB is equal to tau, you have to keep, right? But this RB is not different. There is a mistake here. Okay. So you have to take this RB as the old RB value, not the updated RB value. So we got R value is equal to 1 and R dash value is equal to 1. So we have to dispatch one AR task against one B task. Now you can see WQ if I is equal to TAR. In the waiting queue, if you found a AR task and R is not equal to 0, R is not equal to 0, what you have to do? You have to put in this queue. Okay. You have to put this WQ of I into Q. This is not double equal to single equal to. Okay. And R value is now, once a AR task is dispatched, the R value is decremented by 1. Now there is no R test. And whatever variable you have taken here, J is equal to 1. So I have increased it to 1 more. J plus 1. Right? So one more, one AR task is now successfully executed. Right? Now, as r is equal to 0, in the next iteration r is equal to 0, you will never get to enter into this loop. So this particular loop, what it will do? It will dispatch only one AR task. Okay, only one AR task, age r is equal to 1. If r is equal to 2, you can dispatch 2 AR task. Right? So now, if you see here, now what is our r dash value? R dash value is equal to a 1. R dash value is equal to 1. So in the waiting queue, what we have to do? I have to find a B task. Let's say there is a B task here. So I have to dispatch that B task. Even if there is a AR task here, I will not give opportunity to this AR task. Right? So if the waiting queue is matched with B task and R dash is not equal to 0, so this queue I will put this B task. And this R dash is now increment to 0 and J is incremented by 1. So J actually counts how many tasks are completed. Right? So initially the J value is equal to 1. Okay, now you can see it is increased to 1 in the previous one, and here also it is increased to 1. So J minus 1 is the number of tasks that is completed till now. So once you define this Qj and this Q, okay, then you have to assign the task from queue to the available resources. Okay, and remove TAR, TB from the waiting queue as well as queue. When they are successfully executed, they are not part of the waiting queue. They are also not the part of the queue. Okay, which you have created in this inside the loop. Okay, and update the WQ and the queue value. And until unless the waiting queue is not equal to null, you have to iterate this process. So the important thing you have to learn here is that you have to determine the rate of arrival. Based upon the rate of arrival, you have to decide how many AR leases you can schedule and or how many B leases you can schedule. Okay, so it may be 2:1, it may be 3:1, it may be n:1, or it may be 1:n also. In that way, you can make a fairness. Okay. So this is the first algorithm which I want to tell you, that is based upon the fairness. You can think about when there are in your system, you have a set of AR leases and set of B leases. You can think about this algorithm which will help you to give chances to some of the B leases over the AR lease. Okay. There is another resource allocation algorithm. Okay, before proceed to this one, if you have any doubt, you can ask. If you have any doubt in the first algorithm, you can ask. Otherwise, I'll proceed to the second algorithm. Okay. So let us proceed to the second algorithm, that is called as posted price model. This posted price model is also one of the resource allocation algorithm. And this posted price model is based upon the very famous Hungarian algorithm, or sometimes we call it as Hungarian algorithm. Okay, Hungarian algorithm. Hungarian algorithm. It is a very famous algorithm in mathematics. So here, suppose you are given with 6 different tasks and you have to assign to 6 different machines. So in mathematics, you have studied one principle that is called as pigeonhole principle, right? In pigeonhole principle, it says that, okay, just like there are, if you see the number of pigeons are more than the number of holes, then definitely in one hole you will find any one hole you will find more than one pigeons, right? If one pigeon is at least available in one hole, right? Like if there are 5 persons are there, right? And you have, let's say, 7 food packets. 7 food packets. So I'll tell you, you have to assign these 7 food packets to these persons such that each and every person will get one food packet. So if you say, let's say P1, P2, P3, P4, P5, and let us follow the round robin order. So I can say 1, 1, 1, 1, 1, 5 packets to the 5 different persons. And another 2% got, let's say, another 2 packet, because total packet is 7. So now if you see the number of food packets with P1 is 2, person 1, second person is also 2, third person is 1, fourth person is 1, fifth person it is 1. Right? So you can say if the number of food packets are more than the number of persons, then at least one person is having 2 food packets. So although when you go for resource allocation algorithm, the number of leases is not equal to the number of clouds. Like in this case, you can say the number of tasks is not same as the number of clouds. Because if the number of persons and number of food packets are same, there is no competition. Only if the number of food packets are more, okay, then only you can think that who will receive 2 packets, right? Like here, if you see, if the number of tasks are more and number of machines are less, then you have to you need a resource allocation algorithm or task scheduling algorithm to solve a particular problem. Otherwise, there is no need of such resource allocation algorithm if number of resources are more but number of tasks is less. Let's say number of resources is 5, number of tasks is 3. So there is no need of any algorithm. You can assign them in any order, you will get solution, right? So normally the number of tasks are quite more in comparison to the number of clouds or number of resources. So here we consider 6 different tasks and 6 different clouds. In fact, we have more tasks than the number of clouds, but at a time you can consider only 6 if the number of resources is 6. If another 6 is there, suppose we have 12 tasks and we have 6 clouds, then first 6 tasks you will consider, then the rest 6 tasks you will consider in the next iterations. Okay, so now you have to go for first if you apply the Hungary algorithm or Hungarian method, you can also get the details. It's a very famous method, so you can get from web, or you can find so many articles are also published based upon the Hungary algorithm, right? So first step of the Hungary algorithm says that you have to find the subtract, you have to find the row minimum. So for each row, you have to find the row minimum. So let us highlight which one is row minimum. If I tell you in this particular matrix, find the row minimum. If you look into the first row, which one is the minimum one? Which element is minimum in the first row? Can anybody tell? Which one is the minimum element in the first row? Okay, you can see here it is 0.23 is the minimum. Similarly, T2 case, if you find the row minimum 0.33, 0.34, 0.12, 0, 0 is minimum, 0.96, 0.96, 0 is minimum, right? If you go for T3, 0.42 is minimum, 0.71, 0.31 is now minimum among these three, and rest are above 3.31, so 0.31 is minimum. Similarly, when you go for T4, 0.67, 0.53, 0.38, 0.23, so 0.23 is the minimum. Coming to T5, it is 0.33, 0.34, 0.12, so 0.12 is the minimum. T6 case, 0.42, 0.71, 0.31, so 0.31 is the minimum. The very first step is you have to find the row minimum. Once you find the row minimum, you have to subtract that from each and every element. For example, if I subtract 0.23 from each element, let's say first row, so it becomes 0.67 minus 0.23, 0.53 minus 0.23, 0.38 minus 0.23, 0.23 minus 0.23, 0.96 minus 0.23, 0.96 minus 0.23. So if you calculate this one, how much you will get here? It is 0.44. Okay, here you will get 0.3. Here you will get 0.15. Here you will get 0. Here you will get 0.73. In last case also you will get 0.73. So you can see the same value is written here after finding the row minimum. Right? Now, if you go for T2, you know 0 is the minimum element in the second row. So if you subtract the 0 from all the elements, you will get the same element. So whatever elements are there in this particular row, it is available here. Okay, so there is no change in the second row. But if you go for third row, the elements are 0.42, 0.71, 0.31, 0.49, 0.96, and 0.96. And if you subtract 0.31 from each and every element, okay, you will get the updated value, right? Like here you will get 0.11, here you will get 0.40, 0.31, 0.30, they are cancelled out. 0.49, 0.31, you will get 0.18. Here you will get 0.5 and 65, and here also 0.65. So if you go for the third row, you will get 0.11, 0.40, 0.18, 0.65, and 0.65 respectively. Now coming to T4, T4 case also you have to subtract 0.23, then you will get these values. Okay, you can see only this value becomes 0. Rest value you will get some value which is greater than 0. Similarly, go for fifth row. In the fifth row, you can see 0.33, 0.34, 0.12, 0.96. So if I subtract 0.12 from everyone, this particular element becomes 0. The rest is greater than 0. T6 case, yes, this value is you can say it becomes 0 and rest value is greater than 0. So in this way, this particular matrix is updated to this row minimum matrix. So the first step is to find the row minimum and subtract the corresponding row minimum from each and every element of that corresponding row. Okay. The main overall idea is that why we are making it, you can see after this one, at least you will find 1 0 in each and every row. At least 1 0. And if there are 10 elements are there in a particular row, you will get more than 1 0. Right? So once it is done, then you can think about the second step, that is called as column minimum. So you have to find the column minimum. Like if you look into this particular matrix, the column minimum is 0.11. You can see these two elements are column minimum. Here the column minimum is 0.22. Here the column minimum is 0. Column minimum is 0. And here you will find, I think, the column minimum is 0.65 if I'm correct. And the next case, the column minimum is again 0.65, right? So once you find the column minimum, again you have to subtract it. So if you subtract for the column 1, 0.44 minus 0.11 is 0.33, 0.33 minus is 0.22, then this is 0, then this is 0.33, and this is 0.10, and this is 0. So this is the updated value you got for after finding a column minimum and subtracting it from corresponding column. Go to C2. In the case of C2, it is 0.30 minus 0.22. You will get 0.08. And here 34 minus 22, you will get 0.12. 0.40, 0.22, you will get 0. I think 18. Then 0.30, 0.2, you will get 0.08. 0.22 minus 0.20, then T6 case you will get 0.18, right? Similarly, C3 case, it will be as it is. There is no need because 0 is there. C4 case also it is as it is. That's why I'm not writing here. But C5 case, you have to subtract 0.65. So I think you will get 0.08. 0.96 minus 0.65, you will get 0.31. 0.65 minus 0.65, you will get 0. 0.73 minus 0.65, you will get minus 0.08. Then 0.84 minus 0.65, you will get 0.19, and 0.65 minus 0.0. Okay. C6 is also the identical column. That's why I think you will get the same value, that is 0.08, 0.010, 0.08, 0.19, and 0. So after this column minimum, you can see in each and every column, you will find a 0 element. See here. Here, if you see, the first column is having 0, 0, 0, and here also 0. Like that, C3, C4 case, here you will get 0, right? And more than one place also, you can get 0. So that is nothing but subtracting the column minimum. First step is to subtract the row minimum, find the row minimum, and subtract it from the corresponding element. Second step is find the column minimum and subtract the column minimum from each and every element. And once you're done with this one, now you have to put a number of lines to cover this 0 element. You have to use minimum number of lines. Like you can say that for each and every column, I can put one line to cover the 0 element. Okay, that is the maximum number of lines. Or you can say I will put a line here for the first row, second row, third row, fourth row, fifth row, sixth row. So I have covered all 0 elements. That is nothing but the maximum number of lines to cover the matrix. But here the question is that what is the minimum number of lines to cover this 0 element? So you can see here one of the possible solution I'm writing here. There is requires minimum number of lines is 4. Okay, you can try that with less than 4 lines, how to cover these 0 elements. You will not find a solution. So minimum number of lines required is 4 only, right? For example, if you see, I can tell you right here there are 3 zeros are there. Here 2 zeros are there, 3 zeros are there. Suppose I will cover this line like this. Okay. And here also 3 zeros are there. So you need one line. Here I can put 1 0 line. Okay. Here I can put 0 line, but again 0 is left here. So I need how many lines? 5 lines. So it is not a solution. You have to try less than 4 lines, because 4 lines already solution is given here, right? So you will come to know, if you try hit and trial method, okay, you will come to know minimum number of lines required to cover the 0 elements is 4. Okay, minimum you require 4 lines to cover all the 0 elements. Okay, so actually the next step of the algorithm says that after finding the minimum number of lines to cover all the 0 element, you have to check that whether the minimum number of lines is equal to the minimum number of equal to the number of rows or not, right? Like here the number of lines is 4, right? How many rows are there? Totally 6. So 4 is not equal to 6. So this says that the algorithm not ends here. You have to reiterate. Okay, if you get the minimum number of lines is 6 and the number of rows is also 6, there you have to stop. Yeah, it is written here. Number of lines is equal to number of rows. If you see number of lines to cover the 0 element is 4, but number of rows in our matrix it is 6. So 4 is not equal to 6. So if they are not matching each other, then what you have to do? You have to add the minimum uncovered element to every covered element. Which one is minimum uncovered element? If you look into this particular matrix, the minimum uncovered element, these are nothing but these are the minimum covered element. Okay, these are nothing but the minimum covered element. Minimum uncovered element means these elements are called as uncovered element. Let me write here. These are uncovered element, and these are the covered element. Okay, so what you can do, so minimum is, you can see in this group it is 0.08. Let me see, is there any value which is below 0.08? No. So minimum uncovered element is 0.08. Okay, so once you find the minimum uncovered element, you have to add the minimum uncovered element. The minimum uncovered element is 0.08. That you have to add to every covered element, right? So as we have found, the minimum uncovered element is 0.08. That we have to actually add to all the covered element. Covered element means those elements that are covered by lines. So you may ask, there are some elements that are covered twice. Like here you can see, if I look into this particular position and these three elements, right? So they are covered twice, right? These elements are covered twice. So if the element is covered twice, you have to add two times the minimum covered element, minimum uncovered element, right? Minimum uncovered element is 0.08. That's why we add that into the covered element. If it is a covered element, you have to add two times. If it is covered twice, then you have to add twice. That's why you can see only these position, you can see there are two times 0.08 is added into this particular matrix, right? So you can see I have also represented it in the form of a bold color so that you can easily identify what are the values added or what are the elements are updated. Like here, I think the value is 0. To look into, yes, the value is 0. Now we have added 0.08, so it is now 0.08. Okay. So once it is done, okay, what you have to do? You have to identify now what is the minimum element. The minimum element, including covered and uncovered, the minimum element you will find here it is 0.08. And 0 is updated as 0.08, right? So the minimum element we found here it is 0.08. Now this minimum element you have to subtract from every element in the matrix. Okay, every element in the matrix you have to subtract. So if you abstract 0.08 from each and every element, okay, then you will get this particular matrix. Okay, like you can see, 1, 2, I can show you, it is 0.33, so it is updated to 0.25. It is 0.08, so it is updated to 0. Okay, so now you have got a matrix where 0.08, okay, that you have subtracted because it is the minimum element in the matrix. Now you can see in the matrix you have so many zeros, right or not? There are so many zeros. So what you have to do? You have to again use the number of lines to cover these zeros. Okay, minimum number of lines to cover all the zeros, right? For example, you can see I have given a solution. The minimum number of lines required here to cover all the values, it is equal to 1, equal to 6. Okay, minimum number of lines to cover all the zero elements is equal to 6. If it is not again equal to 6, then you have to reiterate as per the Hungarian algorithm. Okay, but as it is equal to 6, in this case, you have to stop. Okay, now you have to find a solution because resource allocation means you have to decide which task is going to be assigned to which cloud. Right, on which task need to be assigned to which cloud. So for example, if you see, for example, T1 case, let us take T1, T2, let me write here, T1, T2, T3, T4, T5, T6. So what this zero indicates? Zero elements indicates that, this zero element indicates that you can assign to that respective cloud. If it is a non-zero value, you cannot assign it. For example, T1 case, if you see, you can assign to which cloud? you can assign to C2, you can assign to C4, C5, and C6. T2 case, it can be assigned to C4. T3 case, it can be assigned to C1, C3, C5, and C6. T4 case, it can be assigned to C2, C4, C5, C6. T5 case, it can be assigned to C2, C3, and okay. T6 case, it can be assigned to C1, C3, C5, and C6. Right? So now, if you look into this particular matrix, right, this particular solution, now you can see T2 can be assigned to only C4. Okay, T2 can only be assigned to C4. But if I assign T1 to C4, then T2 will not get a chance. Right or not? So T2 is assigned to C4. That means C4 option is eliminated from other tasks. So our solution is T2 should be assigned to C first. Okay, because it has no other possibility. Right? Now, let us see those tasks are having less number of alternatives that you have to think first. Like T5 case, if you look into T5 case, T5 has two opportunities, C2 and C3. Suppose you have decided that let us assign it to C3. I'm assuming, right? So if T5 assigned to C3, that C3 option is not applicable to any other task. Right? Now you can see T1. Now let us go for T1 because all are having three choices. So T1 can be assigned to C2, right? So the C2 option is not applicable to others. Now coming to T3, T3 can be assigned to C1. So C1 option is not applicable to others. Similarly, T4 can be assigned to either C5 or C6. So if you assign it to T4 to C5, then T6 can be assigned to C6. So this is one solution. Okay. And if I ask you what is the cost, then you can say T1 is assigned to C2, right? So this 0, this element. And T2 is assigned to C4, this one. T3 is assigned to C1. And T4 is assigned to C5. T5 is assigned to C3. T6 is assigned to C6. This is the solution. So if you go back to the initial matrix, okay, so this is the solution. So we represent 1. 1 means the allocation is done to the respective cloud. Right? 1 indicates that we have assigned to the respective cloud. 0 indicates that we have not assigned to that particular cloud. Okay, or it is not applicable. Like if this solution, if you see this particular solution and go back to the previous one, for example, let it be this one. These are initial metrics, right? And we found that T1 is assigned to C2, T2 to C4, T1 to C2, T2 to C4, right? Okay, then T3 to T3 1, 5, 3, 6. I'm noting this one. C1, C5, C3, C6. 1, 5, 3, 6. 1, 5, 3, 6. So now, if I ask you what is the cost for this matrix if you solve using Hungarian algorithm, so it is nothing but 0.53 plus 0 plus 0.42 plus 0.96 plus 0.12 plus 0.96. How much you will get when you calculate this one? How much you will get? 0.53 plus 0 plus 0.42 plus 0.96 plus 0.12 plus 0.96. You will get the value is 2.99. Okay. So in this way, you can calculate the results in a Hungarian and matrix. Okay. So if you find a solution which is below this 2.99, then obviously that solution is a better solution. So what I can do, there are so many simulators are also there. Like if you go for Hungarian algorithm simulator, then you can find a lot of simulators. You can find also code because it is a old algorithm. It is written solve the assignment problem online. Okay. So just a try. Let us see. Let us put all the values here and see what is the minimum cost we can get. Okay. Just a minute. Yeah. There are so many calculators you will get. Not necessarily you will use this calculator. Lot of calculators are there. Okay. Let me enter the values. First one is 0.67. It's not fitting here. 0.67. Okay. Yes. Now it is coming. Next one is 0.33. Okay, next is 0.42. Next is 0.67. Next is 0.33. 0.42. Okay, then 0.53. 0.34. Whatever matrix you have given input, I am entering that matrix here so that we can calculate what is the optimum cost. 0.34 and 0.71. Okay, second matrix is done. Third matrix is 0.38, 0.12, 0.31, 0.38, 0.12, 0.31. Next is 0.23, 0, 0.49, 0.23, 0.96, 0.49. Okay. Another two rows are left. Yeah, now you can write 0.96, 0.96, and 0.96, 0.96. So all values are 0.96. I think all rest values are 0.96. Okay, there is no need to look into that matrix. We can directly write here. Okay, I have entered the matrix. If you want random cost matrix, you can click here, right? If you want to see the hands-on calculation, you can generate a random cost matrix by clicking here and solve that problem using Hungarian matrix. Okay, if I click solve, these are solutions, step-by-step solutions are also given. So we are getting the value. What is the value we are getting? 2.99. I already told you what we got here, 2.99. Exactly, it is matching whatever value we have calculated through hands-on calculations. Okay. In fact, you can see the first task is assigned to the second cloud, and the second is assigned to the fourth cloud, third is assigned to the first cloud, fourth is assigned to the fifth cloud, fifth cloud, fourth is assigned to the fifth cloud, fifth is assigned to the third cloud, and sixth is assigned to the sixth task is assigned to the sixth cloud. Right? Row represents the task, column represents you can say that is resources or clouds, right? So you got 2.99, right? So let me share this in that box. If you want, you can go through it. Okay, you can just click. You will get with field value. Just click solve. You have to click here, solve. then you will get the details of matrix with total cost. Optimal value will get 2.9. So there is no value, there is no solution you will get below 0.99. Okay, it is not possible to get the value below 2.99. It is the optimal value. Okay, is it clear? If you have any question, you can ask. Okay, this is all about the resource allocation algorithm. I'll tell you some other theoretical aspect. Just a minute, let me open that PPT. Okay, so now we'll discuss about the resource management in much more details. The theoretical aspect we'll see some of the concept. Here also we'll find some problems that we'll discuss. Okay, so we know that there are different resources we have in cloud computing. That's why we need to manage these resources, right? In resource allocation also, our objective is to allocate the resources to the uh, the leases, right, or the task or to the customer requirements. So there are different type of resources we have, like our computers, like laptop, phones, tablets, desktop, servers, workstations, supercomputer. Anything can be considered as a resources. So we have a three-layer architecture. You can say infrastructure followed by platform. On top of the platform, we have application, right? So there is a three-layer architecture. So generally, the hardware part is associated with the infrastructure and runtime environment. And if you talk about database, if you talk about storage, object storage, then all are considered with platform. An application is nothing but the APIs or user interfaces, or you can say specific applications, monitoring anything, or dashboard kind of things that can be considered as an applications. So what we can say here, the resources are categorized into two different types, right? One resource is called as physical resource. I told you, we call repeatedly it is a virtual infrastructure, right? Because for the customer, it is a virtual infrastructure. But when you go for the provider end, it is not virtual. Provider has to deal with the real hardwares. So if you talk about physical resources, we can use computer, we can use disk, database, network, any scientific instruments associated with nowadays people are integrating with the IoT devices. IoT devices are generating the data and they're pushing this data to the cloud, right? So these all are called as the physical resources. But once these resources are available, so you can once you get the customer requirement, you have to execute it, and you have to look into how many requests you have received and how many requests you have honored, how many requests are executed as per you can say as per the timeline or deadline, or whether it is a time critical application or deadline sensitive application that you have to think. So this execution, monitoring, and communicate applications, they are part of the logical resources. So what we can say, the term actually the resource management refers to the operations used to control how capabilities provided by cloud resources and services can be made available to other entities, whether users or application services in an efficient manner. Whether your infrastructure require this or whether any applications require it, whether your database query requires some resources, whatever manner, right? You have to provide these resources in an efficient manner, managing the resources. Like I can give an example. You have resources to manage, let's say, 10 different customers, but you have designed a very nice policy, okay? And using that policy, if you can manage 12 different customers, so obviously that is a better resource management policy in comparison to the previous one, because expanding the infrastructure is one of the solutions. If the number of users are increasing, we have to increase our infrastructure. Okay, we have to add resources to our infrastructure. But without adding, if I can manage the resource, manage the customers, then really that is an efficient resource management algorithm. And also we need to think about the data center power consumptions. Like if you see the report produced by NRDC or the report produced by international data corporations or many agencies, you will see the number of data centers are in millions, right? Some millions data centers are there. So these million data centers are actually consuming a huge amount of energy. So currently, if you see, it is estimated that the servers consume 0.5% of the world's total electricity usage. Generally, the electricity is also generated using the coal, also with some non-renewable resources, right? So total energy consumption is 0.5. It is maybe old data, but you can see in the current data, you will see it is also a considerable amount of the whole world's electricity usage. Okay, and server energy demands doubles in every 5-6 years, right? Due to compactness of the devices, or you can say due to the factors associated with the hardwares. So always the energy demand increases in a couple of years. So, and also you can see this results in a large amount of carbon dioxide produced by burning fossil fuels. Okay, fossil fuels is nothing but non-renewable energies like gas or petrol or diesel. These things are called as fossil fuel. So they actually generate a large amount of carbon dioxide. So what actually we need? We need to reduce the energy used with minimal performance impact. So if the carbon dioxide generation is more, it is also impacting our environment, right? It is not only impacting environment, but cost-wise is also it is very high, and managing it is also very difficult, right? And over a period of time also, who knows that after 20 and 30 years these resources becomes available or not, right? So we need to reduce the energy without compromising the performance which we are giving to the customer. So there is main motivation of going from the data centers which consumes huge energy to the green data center. So there are two benefits. Economically also you can benefit, because initially for infrastructure cost may be very high, but over a period of time the economic cost becomes low. Like new data centers run on the megawatt scales, requiring millions of dollars to operate. And every time we are adding new data centers, Amazon is adding more availability zones. Okay, putting these availability zones in different regions, right? And recently, institutions are looking for new ways to reduce cost. Okay. Like many universities, institutions, or any organization also, they want that how the resources becomes available without paying much amount. Okay, we are using the terminals, right, in order to access the instances. But actually, the running of the instructions, these all are going on the cloud, so they have to pay that charge. And many facilities are at their peak operating stage and cannot expand without any power sources. You can manage the resources with a certain limit, But once you exceed that limit, it's difficult to manage, right? You cannot expand it. Looking back to the environmental factor, majority of energy sources are all fossil fuel. Still now also, all of electric vehicles are now coming into picture. Now people are also heading towards such type of vehicles rather than using the vehicles which are operated using fossil fuel. That's why you can see fossil fuel are going to be finished over a period of time. So that's why we are moving towards the electric vehicle. But it is really challenging with also with the electric vehicle how you are going to manage the resources. So huge volume of carbon dioxide emitted in each and every year from the power plants. That's why nowadays we look into smart power, we look into smart grid to provide the solution. And sustainable energy resources are not ready. So we need to reduce in energy dependence. That's why we need to go for the green data center. Although the cost is initially high, but the cost can be like you are purchasing a battery, the battery cost may be high, but over a period of time you are using the same battery, that is rechargeable battery, right? So the cost is going to be reduced over a period of time, right? Initial cost is very high. Capital cost you have to spend more, but over a period of time you have to minimize. Only the cost is going to be managed, right? Or averaged, you can say. So advanced scheduling schemes to reduce energy consumption is required. You need efficient scheduling schemes so that the energy consumption is going to be reduced by the help of that schemes. So such schemes can be of two types. They may be power aware, they may be thermal aware. Okay, thermal means it is heat, right? Power means it is related to when we deal with utilization, we call that as energy, right? So we can think these algorithms with respect to the power or also in terms of thermal. Similarly, the performance and what is not following the Moore's law, right? You know the very famous Moore's law, right? So, but as per the Moore's law, you can know that the observation that number of transistor in an integrated circuit, which is doubles in every 2 years, but the performance whatever we are looking that is not following that Moore's law. Okay. So data center design to reduce the power usage effectiveness. Not only data center while you are designing, you have to look into power, but also you have to see the associated activities. In order to maintain the power, you have to also look into the cooling system, managing this data center, managing the resources in the data centers, or you can say server in the data center. How to actually conserve energy within a cloud environment? The first one you can think if you want to do further research work, you can say schedule VMs to conserve energy. While you are dispatching the virtual machines, you have to think that which physical machine is more suitable to accommodate that particular virtual machines. So it is a very burning topic in cloud computing. Many works are also done by various researchers. Similarly, management of both virtual machine and underlying infrastructure. Again, the physical machine managing is important. Like in the previous slide, I mentioned about rack design. Data centers are, the servers are placed in a rack, right? Just like in library, we are putting books. So how you are going to actually manage the VMs and the infrastructure, mapping between the VMs to PM, okay, or mapping between the customer request to the virtual machines is really challenging. And minimizing operating inefficiency for non-essential tasks. Sometimes a particular task wants to utilize more resources and resources are not available. Sometimes it has taken more resources, but it is not properly utilized. You have to also look into that. Similarly, overall, you want to design a data center which will optimize not only one parameter, but a group of parameters. Yeah, if you want to go for energy efficiency, you can see this is the complete, you can say state of art. Like green cloud work, you can look into two parts. One is virtual machine control. You can go for data center design. In order to control the virtual machine, you need scheduling algorithm. Scheduling algorithm may be power aware or thermal aware, as I said. If you look into management aspect, you have to look into VM with virtual machines image design and migration. Similarly, if you go for data center design, it is server and rack region, actually how to place the physical resources. On the other hand, you have to focus on the air condition, that is cooling part or recirculations. Like there is a CRAC unit. Okay, in data center, you will find there is a CRAC unit. Okay, so what this actually CRAC stands for? That says that computer room air conditioning unit. Okay, so this unit is you can say which is used to monitor and maintain the temperature in a data center. And how to maintain cool infrastructure in the data center. That is, it talks about air distribution, talks about humidity in the data center, or you can say network, or you can say server room, right? So for that, you need air condition and recirculations, and also sometimes we look into dynamic shutdown. Okay, like if a resource is not properly used to, we can migrate the resources and immediately we can put that in switch off mode. Now here you can see virtual machine scheduling on multi-core system. Like x-axis, you can see number of cores, right? Number of processing cores. So I've taken the number of processing cores from 0 to 8. Y-axis represent the watts. How much energy or how much power is required if you increase if you want to increase the number of cores. Like you can see when the number of cores are less, like 0, 1, 2, the watts is less. Okay, but when you increase the number of cores, again, this power and energy consumption is drastically increased. So what you can see, it is not a linear relationship, right? Increasing the number of physical units or cores in the same way, the consumption is not increasing in a linear way, right? Like here they have experimented the power consumption for they are calculating on an Intel Core i7-920 server, which is having 4 cores, 8 virtual cores with hyper-threading. So you can see that core whatever we are getting, that is not a linear one. But earlier people think that if one resources I am using, this much is the consumption. Then if I am using 3 resources, it is multiplied by 3. So the relationship is linear. But there is a non-linear relationship between the number of processing cores and the power consumption. That's why we can schedule the VMs to take advantages of this relationship in order to conserve power. So we need to schedule the VMs in such a manner that it can take advantages of this relationship in order to conserve power. Like I may ask a question that if one particular server, okay, if you consider 2 servers, let it be S1 and S2. If I take 2 servers, one server is, let's say, handling 40% of the load, and another server is taking 30% of the load. Okay. In another scenario, S1, S2, they are 2 servers, and S1 is taking 70% of the load, and S2 is completely idle. Right. So if you consider both scenarios, right, I may ask you which scenario is better, right? Whether migrating the load into a one server and making another server is idle is a good solution, or 40% to one server, 30% to another server is a good solution, right? So that you need to analyze, right? That purely depends upon this relationship, whether it is a linear one or it is a non-linear one. Okay, so you can see here one of the very popular algorithms that is based upon the power. I told you there are 2 types of algorithm. One is power ever scheduling. You can go for thermal ever scheduling. Here we will discuss the power ever scheduling algorithm. So the aim of this algorithm is to schedule as many virtual machines at once on a multi-core nodes. Okay, so through this algorithm you can able to manage multiple virtual machines, right? So obviously, sometimes we use here greedy scheduling algorithm. Most algorithms are greedy only, right? And this scheduling keeps track of number of cores on a given node. Like if you are using i3 processors or i7 processors, you have 2 to 4 cores, right? And we match the VM's requirement with node capacity. Whenever you want to place a particular virtual machine, you have to look into their capacity. You have to also look into your server's capacity, right? You have to match the requirement. If the requirement is matched, then only you can provide the resources. Okay. So see here, there is a pool of resources. So for I is equal to 1 to I is less than equal to pool. So we consider I is equal to 1, there is a loop, okay, up to the number of resources that is available. So we consider the number of cores in a pool I, right? So in each and every pool, you have number of cores that you have to find and you have to store in PI, okay? So this is the for loop. For that you have to iterate to know that how many cores are available in each and every node. Then while true, this condition true, okay, there is no specific condition. For I is equal to 1 to I less than equal to q. Now we are finding the q length, okay. So from qy, when I is equal to 1, we looking into first element of the q that we consider here as a virtual machine, right? And for j is equal to 1 to j less than equal to pool. Now you can see you are in a inner loop, right? So under a particular, you can say here we maintain a queue, right? Queue is nothing but a set of VM request. Whereas you can see j, that is the second inner loop, is used to allocate the resources. So I'm checking here if PEJ is greater than equal to 1. Suppose you have multiple nodes under multiple cores under a particular node. So I'm checking if the number of resources is at least 1 or more than 1, then I'm going to check the capacity of the virtual machine on that element, a processing element, you can say. Okay, if it is satisfied, the capacity is matching with the processing element capacity, then I can schedule that particular virtual machine on the processing element. Okay, and number of processing element, it is going to be decremented by 1. Suppose you have 4 different cores. I have assigned one core. Okay, I have taken the resources of one core, then the number of cores left is 3. Okay, so similarly, this process is continued as long as your queue is empty. You have to execute this particular process to dispatch the virtual machines to the resources. Now let us see an example to clear this idea. Here I have given 2 different examples. Okay, there are 2 different examples you can see here. So there are 4 nodes we have. First node says that it is going to consume 170 watt per virtual machine. Second node is consuming 105 watt. Third node is consuming again 105 watt. Fourth node is also consuming 105 watt, right? So I told you under a particular node, you can put multiple virtual machines, right? Like a node consists of multiple cores, multiple resources. In that you can put virtual machines. In the first situation, you can see I have 4 nodes, but I am not utilizing all the 4 nodes. I am only utilizing the first node, and rest nodes are completely idle. I deployed 8 different virtual machines in node 1. Okay. So if I deploy 8 different virtual machine in node 1, so this virtual machine, each and every virtual machine requires 170 watt. They consume 170 watt, right or not? So total power consumption, you can calculate 170 watt into the 8 machines. So 170 watt into 8. How much you will get? Okay, how much you will get if individual it is 107. So let us see how much we are getting. 170 into 8. You will get 1360. If individual it is taking. Or you can say if a ideal node, okay, this is one calculation. Another calculation you can say one ideal node is taking 105 watt. And in a BG node means a node who hosts the virtual machine takes 170 watt. So if you take this one, this is ideal node, this is also ideal node, this is another ideal node. So ideal node into 3, right? 105 into 3, right or not? The 3 ideal node. 105 into 3, it becomes 315. Okay. The BG node is having 170 watt. So I am taking 170 because there is only one node which is BG. Okay, irrespective of the number of virtual machines. Like here I put 8 virtual machines, it is 170 watt. So total, if you calculate, it is 5, it is 8, it is 4. So total, it is consuming 485 watts, right? Which is written here. Okay. You can think with respect to virtual machine, or you can think with respect to node. Previous calculation shows with respect to virtual machine. It is with respect to node. Now, if you compare this situation with another situation where there are 2 virtual machines in each and every node. Okay. If 2 virtual machine in one node, let's say the node consumes 138 watt. Okay, here also you can see there is 2 virtual machine, it consumes 138. 2 virtual machine, 138 watt. 2 virtual machines, 138 watt. So it is total 138 watt into 4. Right? 138 watt into 4. If I do it, 138 into 4, it is 552 watt. So in this example, you can see if you compare the scenario 1 with scenario 1 where a node is heavily loaded and other nodes are idle, then the total consumption is, you can see, the idle nodes are also consuming energy. Okay, that's why you can see that's why other nodes are also consuming energy. But if you calculate the total one is 485, which is more. Okay, not it is not more. It is not more in comparison to scenario two. Okay, okay. But if you go for individual virtual machine, who knows whether the value may be more than of that, right? So it is better to load one particular, in this scenario. If you conclude, then you can say it is better to load all the virtual machine in a particular node and make other nodes idle. Then it is consuming 485, which is a better solution. Scenario 1 is better. Okay, scenario 2 case, it is 138 into 4. So that is 552 watt. So it is consuming more energy. So it is better to load a node with as many as virtual machines are possible. Okay. But if you equally distribute virtual machine into different nodes, then that is not a better solution. Okay, now suppose I'll tell you another scenario. Like suppose each and every virtual machine, okay, let's say if I take another scenario, which I told you previously, suppose each node is taking 170 watt. Here, each node is taking 170 watt. So it is 170 watt into 8. Okay, if a system is ideal, it is taking 105. So 105 into 3. This much is the energy consumption. Here I have taken individual, right? So in this case, it is 138 into what? It 2 in the first case, and all the nodes case it is same only. Okay, so I can write multiplied by 4. So if you calculate this one, calculate it. 170 watt into 8 plus 105 into 3. So it is consuming 1675 watt if I calculate individual virtual machine. But in this case, it is coming as 138 multiplied by 2 into 4. So it is consuming 1104. So if I consider this example in this manner, what is the conclusion? The conclusion is scenario 2 is better than the scenario 1. Okay. But if you consider whole node wise, 485 watts versus 552 watts. So obviously 485 watt is better. Right? So this is the only difference. Like this way, you have to make a comparison, right? Okay, you have to make comparison to know that which solution is actually better. Okay. Now let us go for virtual machine management. Okay, managing the virtual machine is important, right? Like sometimes whenever you are creating a bucket, at that time it is asking you, if you have earlier bucket, if you want to enforce the policy which is uh, enforced to, which is applied to that particular bucket, the same configuration you can copy to your current bucket, right? Similarly, managing this virtual machine, whether you need a predefined virtual machine or you need a virtual machine with specific configurations that you need to define. So monitor cloud usage and load. Cloud is nothing but a set of virtual machines. Virtual machines are a part of our physical machines. So you have to monitor the usage of them in order to determine the load of the cloud. When load is decreased, suppose load is decreased, like in this situation, you can see, assume that in second scenario earlier, or in the uh, first scenario case, you can see node 1 is having 8 different virtual machines. Node 1 is having 8 different virtual machines. Second scenario, you have 2 virtual machines per node, right? And you thought that why not migrate all the virtual machines to node 1. Okay, sometimes we are doing that one, right? So as the load decreases, what you can see, you can migrate the load from one node to another node, right? So slide migrate the VMs to more utilized node. Like here you can see, these are two per node. I have migrated it to node 1. Okay. So in order to, as the load is decreases, I have done this one. And I have shut down the node 2, node 3, and node 4. Again, if you shut down also, uh, these powers are saved. The number of, you can say 105 cross 3. So that is 315 watt is saved, right? But in this case, these nodes are active. So you have to, you are consuming power, okay, in the second scenario. Now, when the load is increased, okay, so in that case, use to start up waiting nodes. Sometimes we have to start the waiting nodes, those nodes which are awaiting. Like here, it can capable of only take 8 different virtual machines. Suppose I got another 2 virtual machines, then I need to start another node. Let's say this is another VM, this is another VM that I have to start, right? And schedule new virtual machines to the new nodes. In this way, you can manage the virtual machine. Now let us see one example to clear this idea. Okay, see here, node 1 is having 3 virtual machine, but node 1 is capable to handle 4 virtual machine. Okay, in the first scenario, you can see node 1 is having 3 virtual machine, but it is actually capable to handle 4 virtual machine. On the other hand, node 2 also capable of handling 4 virtual machine, but currently it is having only 1 virtual machine, right? So migrating from node 1 to node 2, it is not a good solution. Because node 2 having 1 virtual machine, if I migrate all the virtual machine from node 1 to node 2, then 3 virtual machine need to be migrated to node 2, which is not a good solution. Right or not? However, migrating the load from node 2 to node 1 is a good solution because there is only one movement from node 2 to node 1. Right? That's why in the second scenario, we decided that in order to switch off the node 2, the virtual machine which is executed under node 2 need to be migrated to node 1. Okay. Second scenario, we have initiated the process of migration. In the third step, what we have now VM is successfully migrated to node 1. Okay. Just like you are sending a packet and you are getting an acknowledgement, right? So here migration is successfully done. Whether it is a hot migration or it is a cold migration, it is already done. Now what I can do in fourth scenario, node 2 I can put in the switch off mode. So the energy consumed by node 2, now it is, okay, now it is reduced, right? So that is obviously a better solution. Right. Now, another case, suppose you want to minimize the VM instances. Okay, you know the VMs are loaded, right? VMs are loaded means VMs are associated with the several softwares, APIs, libraries. That's why they are loaded. So it also contains some unwanted packages. So such unwanted packages you have to remove from the virtual machines to make it lightly loaded. Okay, and those services are also not required. That also you have to remove in order to make it lightly loaded. So are multiple applications oriented or not service oriented? Okay, you can run multiple applications. Okay, but if a particular service is not required, that you have to actually remove in order to make it lightly loaded. So clouds are based on, you can say, service oriented architecture. So the background of cloud is our service oriented architecture. So those services which are required nowadays, we say about the microservices, right? We are not looking into heavyweight services, rather than we go for microservices. So we need a custom lightweight Linux VM for service oriented service. Like when you are installing Amazon EC2 also, it is asking you different type of VMs to Linux VM. You can see different, even if Amazon also provides its own own operating systems, okay, to provide services to the customer. And it also needs to VM images as well as possible to reduce the network latency. Our overall objective is to manage the latency. The delay should be as minimum as possible. So in that way, you can minimize the load of a particular virtual machine. Okay. So these are the things that are associated with the resource management. We have already discussed some of the algorithms, and these are also some of the important concepts that you have to go through in order to understand the resource management policies. Okay, we'll stop here. If you have any question, you can ask.